Our next paper is applying overlay networks to the smart grid and energy collectives. The presenter will be Lasse. Orda.
Hello.
Yeah, right here. Lasse Orda is a PhD student at the Department of Electrical Engineering at the Technical University of Denmark, DTU. Background is computer science with a master degree in computer science from DTU. His research topic, his PhD research topic, is to investigate technical options for distributed provider and the servers agnostic communication between the power systems and types based on the self-maintaining overlayer network. So, Lasse Orda, are you there?
Yes.
Yeah.
Yep.
Can you share your slides? Okay.
Yep.
Yeah. Okay. Thank you. And we can start now. So please keep your time within 15 minutes. Yeah. Perfect. We can see your slides.
Okay. Hello. I want to talk about how all networks can be applied to the smart grid and energy collectives. So, what is all of this about? Well, an all network is peer-to-peer technology, and it provides discovery of peers, routing, and decentralized communication. This is something that prosumer can use who wants to trade energy directly with peers. It can be used in decentralized energy markets, and it can provide increased local autonomy. For example, if you have DERs and you want them to operate together without having to go through a central hub or actually have human interaction, then we could use a distributed communication network to kind of operate by themselves. Often when you hear the topic of decentralized energy markets, often you kind of fall back to this mystical agent platform, and basically an all network is sort of what often underpins an agent platform if it has to be decentralized and distributed. So in our work, we have improved sort of the efficiency of an all network by using the physical properties of the smart grid. So we were able to create a location-aware heuristic, and which increases efficiency quite a bit, but it has some problems. And to solve these problems and also again increase efficiency, we use complex network theory to kind of model how we store the nodes and how we can connect to them and so on. And finally, we use energy collectives, we use the topology of energy collectives to further enhance peer discovery. Yeah, Jay already introduced me, but basically I sit in this smart grid laboratory that we have, and I also collaborate with the project called the Energy Collective, which is basically a live lab for an energy collective. So all of my work and looking into all networks, I mean, actually use it physically in the real world in the living lab and actually in a smart grid lab. So to put this work into like a smart grid context, well, the work is sort of focused on DERs and prosumers, and you would find it in substation and customer premises, and of course, it involves the communication layer. So, energy collectives. Well, energy collectives are sort of by nature, they want to be self-sustained, and they would like to have their own, they would like to trade energy with themselves and maybe with others, and of course with the system operator, and using an all network would be something that would really support this model. I want to make a quick note about blockchain. Basically, a blockchain is also a decentralized sort of database. You can even make this distributed applications, but as we all know, blockchain is quite slow. So if you have a distributed, like an energy collective, a lot of units, an OLED network can provide the fast response time and the fast controllability that you need to actually work with your units, and it is also able to sort of make a discovery of the other peers in the grid, and then you can combine this with a if you want to stay completely decentralized on your electricity market, you could combine it with a blockchain which is decentralized, but of course you don't have to. But this is where the OLED network would fit in that context. So a quick history of the of peer-to-peer networks. Basically, in the beginning, you had a centralized peer-to-peer network where you had a central server. It breaks, you lose all of your network. Then the next iteration is unstructured peer-to-peer, where all nodes just talk in each other's mouths, and nobody can hear anything, and it breaks. And the third iteration is this called a structured peer-to-peer, and it's based on a distributed hash table, DHT, where each unit has an address which is completely random, and the way you sort of calculate the distance between nodes is it's based on the network that you use, but in Kademlia, which is a well-known network, and which is what our work is based on, they use an XOR on the address, and you get a number, and it's basically a sort of a logical distance between nodes. And this is basically saved in a single dimension. You only have an address, which is a single string of numbers. And this is interesting because when you want to make a location aware heuristic, you have an X and an Y position geographically, which means that you can no longer use sort of the routing table that comes with a default, the standard OLED network. Now, a location aware heuristic, I have an example here, standard OLED network, when you want to go from the start to the end. If you want to find this end node and you're placed in the start, it sends out queries in every direction, outgoing in parallel. And this can be improved by making a directed overlay, by having the location, you know, sort of where you want to go, and you can focus your search directly going to the target you want to see. However, I hope you can see this laser pointer thingy I have. Let's say you are located here, and the end would be up here. Then because of the heuristic, which would just be based on a simple Haversine distance, so it doesn't like to go backwards. It would sort of go this way, and it would get stuck. It would not be able to track backwards and sort of find the correct way up to the target. So this is where the complex network model theory comes in. Basically, the way you solve this issue is by having random nodes that you can use as well. Because if you have a random, if you're standing here and you go up there and you can't get further, then you have a random node that is placed here. Then you can kind of jump to that, and then you will find your way. And this actually improves query efficiency in an OLED network very much. So the random neighbor, basically, every time you learn about a new node, you just save it into your list of nodes. And in our design, we have rate limited this, so you don't get new nodes all of the time. But actually, the first model is called local neighbors, and this is the most basic one. Basically, you save every node that you meet, and when you search for something, you go and ask your nearest neighbor, do you know where this node, this target is? And then he says no, but maybe one of these, and he finds the nodes that are closest to your target and says maybe one of these knows it, and he gives you a list, and then you ask the next node in the list, and so on. You move forward. This is a bit slow. So when you have random neighbors, it enables you to kind of jump around the network, and you skip a lot of the queries, and you save a lot of time. And finally, we have the random hubs. Basically, when you have a lot of some nodes in the network, they sort of, a lot of nodes begin to learn about some nodes in the network, and these nodes becomes hubs because of this. And if you have hubs, you can ask, they know a lot about nodes around them. So your efficiency when you kind of jump to a hub, you can very quickly find the nodes that are related to that hub. And the final, and what we also looked at is using the energy collective. Energy collective, let's say this, it's basically a way to reduce the search space, because you add a property of an energy collective and you're able to search a much smaller address space. This, however, turned out to not exactly improve, but it did result in the revelation that it doesn't slow down your search. You can actually add a lot of different sort of properties that you want to search in the network without issues using this kind of design that we have made. So to test these this out, we have simulated a lot of queries, and we used the European, the IEEE test feeders, the low voltage one, and the 8500 entity, which has 2500 nodes, and then we used a sort of a generated geometric network. Because if you think about it, these test feeders, they're not exactly what you would expect when you think about computer networks. Because these are basically, they're serially linked now. You have like one node and it knows two neighbors and so on. So we also want to try something that resembles a real network like the internet a bit more. And this geometric scale-free network actually has the properties of small world networks as well. As you can see, most of the node has 3 neighbors, and some of the nodes has more neighbors. So the nodes with more neighbors would be the hubs, and so on. So actually, so this means that we have sort of a reference to a real network as well. And what we did to test this is that we made a lot of random starting points and ending points, and we made queries into the network. And of course, this is very random, so you can't just compare the results. So you have to normalize the results. And this is what this perform efficiency factor is. Basically, we use Dijkstra to actually find the fastest path through the network, and then we compare that to the actually test query and sort of divide them into each other, and you get a normalized number. So what we're looking at here is up here we have the standard OL network, the Kademlia, and here we have the improved efficiency multi-dimensional network with the location-aware heuristic. And as we can see, it performs quite a lot better. Also, the Kademlia sort of plateaus, but the multi-dimensional OL network actually continues improving as sort of random hubs are generated, and it can continuously improve efficiency. Another test is actually this one right here on left is with the complex network theory, and below here, and these up here are not using complex, so it's basically heuristic only up here. And as we can see, they go a little sort of improve, and then they come bad. And basically the reason is that with the heuristic and no support from the complex models, as the OL network learns about more and more nodes, actually it fails and it gets stuck and it can't find the target. So it has a lot of misses. So the second part of this design is quite important. What we see over here on the right top is the application where OL network versus the network with the energy collective topology included. And as we can see, well, they are basically on par. But what it shows is that that we can add multiple dimensions to the network and the routing, and it will still be efficient. So it's actually quite difficult to balance the properties if you want to make a multidimensional identifier, because let's say you have a physical location, XY, then how would you correlate that with something like flexibility? So that's quite difficult. I mean, so the energy collective topology is still sort of a physical location-based sort of identifier. So you have to think about what properties you want to use. You can, of course, do something like ask, I want these nodes in the network with this flexibility available. But you have to balance, maybe ask for the location first and then ask for the flexibility in that area. So you can have something like location-based services. So actually, as well, we talked about reducing the search page by using the topology, did not yield an improvement in efficiency, but well, we can use multiple properties without performance loss. So right now the design we have is using sort of, well, not stupid, but simple lists for all the nodes that it knows. And when you kind of query for a node, you go in and you ask your storage for the closest nodes to your target, and it has a time of ON. And if you use something like a KD3, which we have tried, you get a lot better performance. Unfortunately, we weren't able to simulate and actually get some results from that for this work. Also using this is something that happens quite often when you do a search for a target node that you want to communicate with. You query this what is called this your lists of nodes very often, and if it's complex to calculate, then it has a computational cost. It wasn't really that sort of noticeable when we did physical tests with real nodes in the real world, but when you do a simulation with thousands of nodes on a single computer, or even a HPC, a high performance cluster, sort of the repeated calculations, they add up. So that's something to say to improve the performance of the calculations. So finally, I would like to say thank you for listening, and the conclusion is that using the properties of the smart grid actually makes it possible to provide location-based services, as well as improving the efficiency of decentralized communication quite a bit. And it enables us to use multiple properties of the nodes in the power grid, and we can find nodes based on the properties, and we can even improve sometimes the search by using these properties. Yes, thank you.
Yeah, thank you, Miss Orda. We have one question here. It's about the hardware of the overlayer network. Can you see that question?
Yes.
Yeah.
Well, there's definitely, I mean, it's not on the power network unless you want to do communication over power networks, but you don't want to do that because you usually use your packets every time you hit a transformer station. But it's basically two different networks. I mean, you have the power grid, then you have the communication network, which would be, I mean, in the old days, you used dedicated tunnels and so on to actually control your power generation stations. But with DRs, distributed energy resources, you now have a lot of resources standing like on your public fields and whatever out in the country, and they're connected with actually just consumer broadband. And this is where all networks actually are quite good, because they provide extreme resilience and robustness in the case of networks that are not optimal, that are actually bad. So that's I mean, that's, I didn't say that, but that's one of the reasons we actually looked into using all networks in combination with the power grids in the first place.
Okay. Okay, thank you, Miss Oda. Your work. I think this is quite interesting work and quite critical work, because now cyber and physical systems are closely tied. So we have to we have not only focus on the power systems problem, also have to focus on the communication problem. Actually, I have quite a lot of questions. Maybe after this session, I discuss offline and send email to you. Okay.
You're most
Okay.
welcome.
Yeah. Okay. Thank you so much. So
Yep.